Tonight we have a good session for everyone on the data cleaning course through Kaggle Learn. If this is your first adventure with us, I'm pleased to be joined by the founder of Deep Learning Adventures, George Zoto, and my co-organizer, David Patton, and I have been helping to organize some of the events here. And we've been fortunate to have a variety of other speakers contribute to our quickly growing group as well. If you'd like to check out some of our past events, you can find a YouTube channel. Let me actually share my screen to show. We have a Slack channel that you should join if you're not there with us yet. We have a YouTube channel here that has most of our past deep learning adventures, including a series earlier this year in TensorFlow in practice, the course offered through Coursera. We also did a variety of coding challenges after that to solve some interesting problems in computer vision, NLP, time series analysis, and structured data set deep learning. And more recently, we've been embarking on an adventure to work through the Kaggle Learn series, a series of mini courses that can each be completed in the span of a few hours, covering just about every topic that just about every general topic that a data scientist or machine learning practitioner should be aware of. And tonight we have the data cleaning course. So I suppose a more fair allocation would be to spend about 80% of our course time doing the data cleaning course. But I suppose that's not actually the way we're doing things here.
Thank God.
So we can get some links for the YouTube and Slack posted. I'll put those in the chat if they're not there already after we get started. It's a fairly small, how many people do we have on tonight?
21.
We have a bit of a shorter session, so I think we have time to go around for brief introductions if people want to just say a few words about themselves and just a bit of background, anything that you're hoping to get out of your adventures with us, and maybe anything else interesting about yourself. I guess I'll start, and let's see if I can, I'll stop sharing my screen so I can see the rest of you. So I'm Robert Craig, a data scientist, originally physicist. I've done some work in defense, education, transportation, finance. Has been able to solve a variety of problems throughout a career, both in academia and nonprofits. And let's move to George. Oh, something interesting about myself. I'm also a musician, piano.
That's the cherry on top of the cake. You're a great musician. Thank you, Robert. My name is George, everyone. I'm a co-organizer of Deep Learning Meetups along with my friends, Robert, David, as well as Dimitri, Liana, and Kathleen, who have helped us recently with many interesting notebooks. Happy to be here. I'm a data scientist and data engineer for a nonprofit in DC called No Kid Hungry. And after my day-to-day work, I also explore deep learning and machine learning concepts using our great community as a platform to learn from each other, support each other, and have fun. I'll pass it on to David.
So David Patton, have a background in scientific research, then moved more into software development field. And now I'm a data scientist, worked in a lot of different domains, but heavily involved now in healthcare. And I'll move on to Liana.
Thanks, David. Yeah, my name's Liana. I'm based in Seattle, originally from Australia. Been here for 2 and a bit years now. I am a job searching data person. say data person because we can have lots of words at the end of that data word. And I joined this DLA group because I think the best way to learn is through community and learning from each other. It's also, I think, the most interesting way to learn and to continue to learn. So yeah, I enjoy this group, and that's me.
Maybe it'll be easier if I just call people in the order that I see them on my screen to streamline things a bit. And if you don't wish to participate, feel free to just move along to the next person. But we'll start with Olivia.
Okay. Used to be a software engineer. I'm transitioning to data science for 18 months now. And I think I'll be looking for something, a job within the next 6 months. I enjoy your meetup. I do attend several of them, and you have one of the best.
Chris Woodard.
Okay. Based in Tampa, Florida. The picture behind me now is actually not too far from my house, part of my morning walk. I've been a software developer for coming up on 40 years, with a couple of timeouts for going to graduate school in psychology, some research background there, and then coming back to it because it's about time for a career change. And he's right. This is one of the better groups out there. What I'm looking to get out of it is partly a community and partly motivation and support to practice. Because I still have a day job as a software guy.
Thank you, Chris. Dimitri?
Yeah, so my name is Dimitri Livonian. I come from a mixed finance and linguistics background. So worked in private equity for 20 years now. And some time ago, I moved into more like NLP stuff, doing sentiment analysis and trying to do trying to go deep into transformers and more advanced NLP techniques now. So I like this meetup. I think the topics are diverse. People are great, so I'm enjoying this community.
Thank you. Next we have Dilip. I hope I'm saying the names somewhat close.
Yeah, hi. Yeah, this is Dilip Rahija from Tampa Bay, Florida. I have a degree in finance, bachelor's degree in finance, and master's in computer science with mathematics. And I spent many years doing the data analysis and anything to do with data. That's my forte. We did a lot of business intelligence, and recently getting involved with data science more and more. And I have spent good 10 years with DoD and some of the federal work. And I do anything and everything, whatever comes my way: administration, data engineering, data science, business intelligence.
Wonderful. Great to meet you, Dilip.
Thank you.
Next we have Kathleen. You're muted.
I'm Kathleen Perez-Lopez. My background is math, and my degrees are math and computer science. I was an image scientist with the imagery intelligence for a number of years, and got interested in deep learning when I saw the convolutional neural networks doing what we used to do in feature engineering and image science. I followed that interest and got into leading a deep learning working group, and which we stopped when we couldn't meet in person. That's how I met George and David and Robert. And I am I guess, recovering entrepreneur. I was involved in a business for a few years, starting up and it's kind of closing down now. So I'm just interested in continuing to learn. There's just so much cool stuff that you can do now that used to take so long, and now it's just really exciting. There's a whole lot of compute power, a whole lot of data, and a whole lot of algorithms and software available. So it's a really exciting time.
Yes, computer vision has changed a lot.
Yeah.
Next we have Jeff O'Connell.
Yes, good evening, everyone. My name is Jeff O'Connell. I'm in the Columbia, Maryland area. I work in academia at the University of Maryland, Baltimore. That's the medical school. My background is math and computer science and statistics. I work mostly statistical genetics, mixed models with large genomic data. And I'm very interested in transitioning from sort of the parametric statistical models into some of these deep learning sort of methodologies that are starting to gain ground in the field. So I've heard some talks on them, and so I'm trying to sort of transition into that area. And this group has been very helpful, although I haven't had the full bandwidth to keep up with all the course work, but I hope to catch up. So thank you.
Oh, wonderful to meet you, Jeff. I would say for me, I would consider deep learning models to be parametric, just with a lot more parameters than you're probably used to.
Okay, thanks.
The next person I see here is Hiten Gajar. I'm sorry if I'm mispronouncing.
You said it correct. Hi everyone, Hiten here. I belong to Baltimore area in Maryland. Been with Fleet Industries and working as a data engineer in my company. And the thing is, I like it in this group about like we can all exchange our knowledge and all. So right, so I want to explore more towards data science. Already working as a data engineer, but want to explore further on that domain. So that's what I like it here. So been hooked up to this group. Thanks.
Thank you. How about Svetlana?
Yes, hello, I'm Svetlana Levitan. I worked as a software engineer implementing statistical and machine learning algorithms for SPSS for many years. Currently, I'm working on a volunteer basis with a small startup doing data science for them, and I'm looking for a permanent position. And this meetup is just great. I'm also a co-organizer for Chicago ML meetup and some other meetups. And but this one is dear to me because I attended University of Maryland a long time ago. And I enjoy this meetup very much. Thank you.
Good to see you again. Next we have Neil. I think you might have joined after we started, but we're just going around introducing if you feel like saying a few words.
Sure, yeah, hi, I did join a little late, but I guess we're doing introductions here, so that's good. Well, I know a lot of people already. I've been doing this meetup for a while now, so, but for those who don't know me, my background is I'm actually an engineer, kind of a hardware engineering background with an interest in computer architecture, high performance computing, and using heterogeneous computing to accelerate algorithms. So, but I've been getting, into deep learning and machine learning recently because it's really fascinating and the applications are tremendous, and it's a good application for the kind of stuff that I do. So I'm always on the lookout to see if there are interesting problems that I can help to apply computing to. So, but this is my favorite meetup. I learned the most from this one for sure.
And Neil is joining us right on the heels of giving a talk at another meetup. Great talk on FPGAs and GPUs and a lot of stuff on hardware acceleration that can be really useful for the stuff that we're learning here. I'm assuming that there's a link to the recording that'll be out at some points, which I'd definitely like to go back to look at.
Yeah,
but,
I missed it. I'm looking forward to the recording now.
Yeah, I'm pretty sure that Chris will put out the recording, so look for that. Thanks.
Cool, thank you. Next we have Muhammad Ali Yusuf. I don't hear anything from Mohammed. So how about Jeffrey?
Hi, my name is Jeffrey. Computer science major. My research background is computer vision. I'm current biometrics SME. Thank you. I would like to learn something, a lot of things from this school.
Great. Next we have EJ. Your name is showing up as just EJ. So I don't hear anything from EJ. How about Chiwan Cheng?
My name is Qiyuan Chen, and my background is physical chemistry, and I'm currently working in the consumer product company, and I'm trying to transition to a data science position, and I enjoy learning new things in this group. Thank you.
Thank you, Chiwan. Next we have Scott Arnold.
Hi, I'm Scott. I realized I didn't have a non-government Zoom account, so I was trying to set it up, but I'm not done. Anyway, I'm working in the government. I work at the National Science Foundation, and been trying to use more data science tools. You know, it used to be called analysis, but I'm using those tools, and I want to learn more. And this looked like a really good venue to get some more knowledge and try and meet it, because I've never done that before.
Well, it's great to meet you, Scott. The next person on I see is username Ashrimram.
He introduced himself in the chat.
Oh, okay. So we can go read the chat there. We can move on to Maria Stoica.
Hi, everyone. My name is Maria Stoica, and I'm a research scientist. I'm currently working remotely for University of Colorado, but I'm located in Virginia. And I'm originally trained in electrical engineering, and I did my PhD in material science and energy engineering. But over the last 4 years or so, I've transitioned into ontology engineering. And I'm working with research scientists in the geosciences. And I'm interested in expanding my work to move into automated ontology generation. And so I've been kind of getting into machine learning and NLP and things like that. So this meetup sounded really interesting to me.
Well, great to meet you, Maria. Next we have Peter.
Hi, I'm Peter. I'm a software engineer. I've been with this group since the beginning, and so mostly I work right now in cloud computing stuff, but interested in learning as much as I can about deep learning. So.
Great, nice to see you, Peter.
Yep, thanks.
How about Christine Tang?
Hi, my name is Christine. I work as a software engineer from 2000 to 2009, then moved abroad for the next 5 years, and I was working on operation management in tourism and hospitality industry. Then I had a long break for 7 years, and now I'm getting ready to go back to work again. And so my friend recommended me this group, the Tech Meetup. So I've been joining for a few months now, and I'm volunteering. I'm doing a volunteer project now that need to do data analysis. So this is really useful. And I'm very happy to be here to get motivated and seeing all the friendly faces. Yeah. So I'm happy to be here, like even, just listening in. Yeah, it's very nice to do this, especially during the COVID period, I guess. Thank you.
Yeah, it is nice that we're still able to do something during this period anyway. It's good to see you, Christine.
Thank you.
Next we have Fatima. I don't hear Fatima. Next we have Madison. We're doing introductions. I think I saw you just pop in. If you want to say a few words about yourself, feel free.
Yeah, so I'm Madison. I work as a data analyst at the DOJ. Meetup actually recommended this group based on my interest in data science, so I've been attending meetups for the past month or so, and it's been really fun and really insightful.
Thank you, Madison. That's everyone I see here right now. Thanks for giving us the chance to go around the room today. I know we've had a lot of really long events recently, and we haven't really had a chance to take advantage of some other aspects of the meetup other than just having people talk at you. So for anyone who hasn't joined, we'll put a join link to the Slack group and the YouTube channel in the chat. But without further ado, I want to move on. Tonight we're working on the Kaggle Learn course on data cleaning, and I believe we have two speakers tonight. Dimitri Livonian will get a chance to hear what he has to say about the first three sections of the course, and then I think David Patton is doing the last two. So the floor is yours, Dimitri. Do we need to make you a host to share your screen?
Yep. Mm-hmm.
Should be able to see your screen.
Okay. Can you see the screen?
Yes.
Great. So this section of Kaggle courses is called data cleaning, and it has five items. So handling missing values, scaling, dates, and so the first three, I'm going to cover these first three, and Robert is going to cover the last two, character encoding and inconsistent data. So let me go to handling missing values. And I mean, we've all seen missing data, and I think we all know how painful it could be. You know, spending a lot of time, especially if the data set is large. Basically, you know, they don't have a very systematic sort of approach here in this section. So I was going to just talk a little bit about the general approach, and then probably go straight to the notebook. So basically, we have a few options with missing data, right? So we could delete them, delete the records, or delete the columns, the features. We could impute the missing values with something, maybe a constant value, maybe, you know, based on the neighboring observations, or we could leave it as it is, because sometimes missing data tells us something, right? So it's not just missing by chance, but it's missing because you know, there was some reason or some peculiarity in the data generating process. So sometimes the missingness itself is a valuable information that we don't want to lose. In this Kaggle page, they focus on the bad part of the missing, like, you know, what should we do, you know, how should we delete them, and, you know, fill with impute with something, fill with you know, some constant values, basically. So the first thing they do is yeah, they import a data set from American football games, and basically that's how it looks. It's a data frame with you know, about 100 columns, game statistics, and the first thing they do is they check how many missing values are in each column. And I should say, is null is the old equivalent of is NA. Pandas uses is NA and not NA. And so basically what this is null produces, or is NA produces the Boolean values, true false for the entire data frame, and some sums in the zero direction, so in this axis, and it gives us basically how many values are missing in each column. And they, just for convenience, they didn't use the entire 100 features, just showing us what's happening in the first 10 features. We could also sum the entire missing data, the missing occurrences in data frame, and see how much is it missing from the total columns, from the total data that we have, and it gives us 25% is missing in this big data frame. Yeah, they discuss a little different reasons why the data might be missing. And we will see more examples of that in the exercise. But basically, they also focus on making distinction between data missing in a bad way. So basically a sensor didn't work, or the person who was doing the census didn't fill out the field, etc. Versus something that is basically the attribute that is missing from the object because the object because of the nature of the object. So they discuss that, and then they go into the whole dropping exercises. So drop NA is basically the pandas method to remove the NA values. This one is removing all the rows that have any missing values, and so it so happened that all the rows, every row in the data frame has at least some value missing. So if you use something like that, you may very well end up with just an empty data frame. So we need to be careful here. And I'll show a more sort of flexible approaches to that. So here they basically try the same with they're removing removing the data that has any missing value in the columns. So the X1 means column wise, and apparently 41 columns are with missing data, and the rest are free. So the rest are they don't have any missing data in the rest, but 60% of the data frame is basically missing fully or in part. Yeah, so that's what they show. From the 102 columns in the original data set, 41 contain missing data. And finally, what they discuss is fill NA. Yes, they do discuss fill NA. So fill NA is, again, the standard method in pandas to fill the missing data with any value. And there are a few methods, a few parameters to fill NA that you can use, and I'll show that in the notebook. But this is the basic. You fill everything with constant values, and 0 is the most common, the default value. One thing I should add is that fill NA would replace, would find all kinds of NAs, which is numpy nan, not a number. The non-value also will be filled, and pandas, some specific NA values specific for pandas, which may not be float 32 as numpy, but some other. For example, it can be NA in the integer 8 format. So this fill NA will fill everything. Yeah, so they show one of the parameters. So the B fill is backfill, basically. which means, if, for example, I have some data tomorrow, but not today, today is missing, so I take the data from tomorrow and impute it for today. Basically, shifting one, is propagating, the future data to the present. Yeah, and let me go straight to the exercise. Oops, that's not it. Yep. Yeah, so in this exercise, they work with the San Francisco building permits. This is an interesting data set. So first thing we do is check the shape, and it has like 200,000 building permits with 43 features, 43 columns. And as we can see, there are already, like visually, we see a lot of numbers in the columns. And so that's an interesting one. So first thing is we check, which columns are missing. And if you do is-NA sum, you see quite a lot. If from 200,000 observations, there are some that don't have missing values, but there are some that are close to 200,000. So a lot of columns have a lot of empty missing values here. And columns include everything from the address information, the information about the building itself, all kinds of structural data, data relating to permits, dates, etc., etc. Some of the missing data is strange. For example, there are missing zip codes, or I noticed there are missing, where was that? Yeah, missing file dates, for example. Oh, no, issue dates. I don't know what that means, but some of the missing data is not usual. So we can do just a very simple transformation to see how much is missing, in percentage terms. And as we can see, so there are some zeros, but 98%, 99%. There's a column of 100% missing, and another one. And this is a short way to sum all the missing, the occurrences. We use two sums, and basically it sums row-wise and then column-wise and produces just a single number of total missing entries in the data frame, and then divide by the size of the data frame, and we get that about 26% of the entire data frame is missing. So now in this section, they suggest that we just think, what might be the reason that the street number suffix or the zip code might be missing. And my guess would be that, this could relate to some, greenfield development, that there is no specific address yet, at the time of getting the construction permit. But the zip code missing, I can't really, imagine the reason why a zip code would be missing from the construction permit. And so I guess, if we would do some sort of, for example, analysis related to location and geospatial something, this would be a big problem. Maybe, the right way would be just to remove these records with missing zip codes. So they ask for us to see, how many rows are left if we drop all the rows that have at least something missing in them. And a quick way to do that is to use this any, the pandas any and all, or actually the Python, I should say. And so basically what this is just basically if any of the columns are missing. This would give us true, and then we sum it vertically to see, if everything, if all the rows have any columns missing. And so the answer is yes. So all rows contain missing data. Now we could use the drop NA to drop, the columns that have missing data, and we could check, how many are there. So we use this syntax, the drop NA access1, and so the drop columns are, we drop 31 columns from the permits. Yeah, this is basically, I did that. So, and so one final thing they try is they fill the missing data with bfill. This is just as an example. This is not a good method here. Probably, fill NA would be fill NA with zeros, or do something else. But basically, what I was thinking about, focusing our attention to is, in time series context, it's very important not to be very careful about data leakage, and not to import data from the future, which is exactly, if you do backfill, you're leaking data from the future observations to present, as opposed to forward fill. It may seem counterintuitive, but at first, but we should take the past data, and then fill them, project them into the present, and not vice versa. So be careful. We only do forward fill in time series. One other thing, they didn't have it here. I just thought this might be useful. There is a useful method called Interpolate, and you just call it like dataframe.interpolate. For example, if we have this sample data frame, and then if you interpolate, it has different methods. You could specify different methods, but in this case, it's just a simple linear interpolation. So between this and this, so between 2.1 and 4.7, it would interpolate with 3.4. So this, is useful in many contexts. Yeah. So that's it. Actually, the pandas fill NA and drop NA have quite detailed help pages. So quite a few useful examples over there. Are there any questions at this point?
Feel free to speak up, everyone, if you have questions, to either speak them out when you have them, or post them into the chat. Not really a question so much, but a comment. I think one message that was implied in the course for this section, but wasn't really made super explicit, is that whenever you're processing missing data, kind of the key thing to think about is, how is the strategy that you're considering doing going to impact any bias that might be in your model. So, you get to the question of, sure, it's easy to just remove values that are missing, but ask yourself, why are those missing? Does that indicate some issue with data collection? Is there a reason that the missing values might be distributed differently than values selected randomly throughout the sample? And that same logic could go for your data set as a whole, right? Why are these samples in your data set? Are there other samples? Is your data set representative of the distribution you're even attempting to model?
And if you're going to have predictions in the future when you roll this thing out in production, are those missing data going to show up there as well?
Right.
Then you really can't throw them out. Right?
Yeah. One thing I should add probably is that I also think about the platform or the algorithm I'm going to use, because if I'm going to use something with TensorFlow or deep learning basically, then it's really important that there are no missing data and there are no nans, because it's going to crash the algorithm. And there are some more robust things, like if, for example, I think the XGBoost is more flexible with that, so it would still work with some of the nans here and there, but not the TensorFlow thing. So it's also important what we're going to use.
I was going to make a comment as well on the data collection front. The is NA can be misleading sometimes too if it says there are 0 NAs, but again, if your data collection could be, however, it could be filling as manual saying none, that's not a pandas NA, or picking up as an NA, or if it's a float or integer just as a 0 when it means NA. So sometimes that can be misleading. So.
Yeah, and two, it could just be a simple miscoding. Yeah, something could have been coded as a string when tried to be interpreted as a float, for example, and it would wind up being imported as an NA.
Yep. So let me go to the second section, and I'll speed up a little. So in this section, they discuss scaling and normalization. Basically, scaling and normalization, they're used interchangeably. In this specific page, they suggest that scaling is basically scaling, and normalization is necessarily trying to bring your distribution as close as possible to normal, which is not the not necessarily the way that we're used to. But in Kaggle, they, for some reason, they follow this semantics. So basically, scaling is a very good idea, and we've discussed this, I think, quite a few times already in this group, right? So many algorithms run more stable and converge faster when the input data is normalized, is scaled. It's also a good idea to do that sometimes in between your algorithms, right in between your stages or steps or layers in deep learning context. Some of the traditional machine learning algorithms that rely on distance data, basically on a distance metric between the data points, such as the SVMs or k-nearest neighbors, they also benefit from scaling, right? Because the Euclidean distance is very much affected by the scale of your different dimensions. And so if, for example, the dimensions happen to describe different sort of units of measurement, then the algorithm is going to run much faster and converge faster if they're scaled to the same units. They use a package called ML extend preprocessing. Many people prefer the standard scikit-learn min-max scaler, myself included, but it probably works the same. They basically bring data in arbitrary units to the 0 to 1 scale, or a different A to B. And they basically show how it's done here. And what they call normalization is basically all kinds of transformations that bring your original distribution close to normal. And then the standard is box-cox transformation, so basically a power transform, right? So especially, for example, if you have things like price data or count data, for non-negative observations, they're usually distributed in a weird, all kinds of weird forms. And then a standard step would be to apply, for example, a log and bring it to more to a normal shape. So that's what they suggest. This is the typical picture you would get, for example, with I don't know what this is, but this is a very typical thing if you're working with the, for example, price data. And so you apply this, and in your algorithms, many machine learning algorithms run smoother and more stable. So let me go to the exercise. Other states. Oops. Oops. Let me open this. For some reason, just I'm sorry.
I think it's your last one right before. Yep.
Oh, okay. Yeah, there it is. So I should say this is not a very informative notebook. So they work with the Kickstarter data frame, and basically, Kickstarter data set has a lot of data related to the dollar amounts, right? The initial goal, and then how much people contributed. And what this notebook does is basically applying all kinds of transformations to those dollar amounts. So that's the syntax I use. Import the min-max scalar from the scikit-learn, and then you feed transform the original data. It makes little sense to actually feed transform price data with the min-max, because basically you don't change the shape of the distribution, and yeah, but that's what they do actually. This is the original data, this is the scale data, zero value added, I would say. It's just learning that this transformation is using this syntax, and they ask us to apply the same to a few other columns, and we get the same picture. This is not really interesting. And now finally we get to the box-cox transformation, which is in general form, it has basically you use some lambda parameter to apply the power transform and divide by lambda. And if lambda is 0, it's basically the logarithm of your input data. So this is very much useful. And we would use that to apply to the pledged, to actually the real pledged amount of the Kickstarter data. And there is a box-cox transformation in the SciPy, and we could use that, and also we could use the logarithm, and I'll explain the difference. So they're using this box-cox from the SciPy, from the I'm sorry, not from the SciPy, from the stats module. And what it does is it transforms the original data to this normalized data. Actually, in stats module, you don't specify the lambda. The stats module selects the lambda so that the basically the output distribution is as close to normal as possible. And so I thought, this is a very interesting thing, but you could also, if you're sure it's sort of log normal, then you could use just the log or log 10 in this case. I use log 10 just to make sense of the numbers. Oh, I didn't import the yeah. So, and we can see that, it's log base 10. So this is, hundreds of dollars and then thousands of dollars somewhere here. This is ten thousands of dollars, etc. And there are a few Kickstarter projects that actually did $1 million and above. But we can clearly see that, this very much skewed and basically mysterious distribution is actually on the log scale. It's quite understandable and transparent, and you could interpret that. And the machine learning algorithm would have a much easier job actually processing this kind of input than this kind of input. Yeah, and then they basically repeat that with a few other input features from the same data set. Not really different. Okay. So any questions on this side?
Just a general question. I haven't used this box-cox before, but I'm curious how it compares to maybe the standard way of removing the mean and dividing by standard deviation on a distribution. I was trying to.
Well, yeah, removing the mean divided by standard deviation, the standard scaling does not change the shape of your data, right? It remains the same shape. It's just basically d means brings you to mu0 sigma 1 situation, but it's still the same shape. Here the shape is changed, right? So if you, for example, take the log, just the whole shape of your data changes. And I just wanted to show that. Can you see my screen now?
Yes.
Yeah. So this was one of the earlier exercise I did. So this is Iowa Ames dataset house prices, and these are the raw prices, very much skewed to the left. And because it's price data, when you do log transform, it becomes very much closer to normal. And I just check it here that the log transform data are closer to normal than the original data. And basically every time you have a picture like this, taking a log is a good idea.
So, Dimitri, I'm glad you brought this up because if I recall right, sales price was the target that we were trying to predict.
Right.
So maybe you could mention to people, we were doing scaling and normalization on the input features, but sometimes, what would be the impact of scaling the target, the labels, and then how do you have to adjust that when you do a prediction to get a real value back? Does that make sense what I'm saying?
Right. Yeah. It does make sense. So basically it depends on the algorithm. So for some machine learning methods, right? For example, for all kinds of linear regressions, for example, what you're trying to find is a linear mapping between the inputs and the outputs, and very often what you have is a picture like this. And so the linear mapping exists between some raw inputs and the scaled outputs, or the logged outputs, and that's the situation when you would take the log. But you, of course, you must remember that you took the log. So whatever your model produces, then you don't forget to scale it back, basically, to take the exponent and recover the original price. And it depends on the. I think it depends on the method you use, right? So, for example, if you would use the XGBoost or any tree-based methods, probably this may not be as useful, or maybe the XGBoost wouldn't care if you scale it to log or not. I'm not sure, but probably it's much less sensitive to all these transformations.
Yeah, it's sort of like it reweights your loss function not to put too much emphasis on those upper outliers anyway.
Yep. So let me go to the last section, and that's about dates. So basically, what they do is they process, they import a data frame that has a date feature, a date column, landslides, which has the column called date and time, and they spent some time actually verifying that it's not in pandas datetime format. It's an object. An object meaning it's a string, probably in this case. And because it's a string, you can do many things, right? You can take a difference in dates. You can sort by date, etc., etc. So first thing we do is transforming this string column into datetime type. And so pandas is very powerful in working with dates. They used to have quite a few problems, like they didn't have convenient methods to calculate difference in dates, etc. But in the recent releases, they provided all the functionality. So basically, the basic method to convert a string date into the date time is PD to datetime. And so our inputs, most of the time, they are strings, right? So whatever data we have in the wild, like if we get a data set, etc., it's 99% of the time it's just in string format. And so to convert that to datetime, we use that. We specify the specific format that our strings come in, and so they, this M, D, and Y correspond to months, dates, and years. M's, capital M is minute, and there's a whole convenient page that discusses all the pandas conventions, and you could do quite a lot here, including, of course, the days of the week, and months in short format and long format, padded format, right? So like January 01 versus January 1, etc. So Pandas has all the necessary flexibility here. And so once we have this, so this new column, landslide date parsed, is not a string anymore, it's a datetime object. And so here's we check it's a datetime. Yeah, so one flexible thing Pandas has is sometimes you don't know the format. Like, sometimes you would get a full description, including the time, and then in some fields there are only dates, etc. And so if that's the case, you could use this. And for smaller data sets with unknown date format, this is fine. But if you have like a large data set with tens of thousands of observations, etc., this is just going to be slow. So you better decide, what the input format is and specify it explicitly. And of course, once it's in datetime, once it's a Pandas datetime object, you could do everything. Differences, etc., etc. Like, for example, one of the examples they have it here is extracting the day information, so the day of the month information from this datetime object. And finally, they just take that day information and plot the day of the month, and those are basically landslides that happen on the 5th of the month versus 30th of the month, etc. Not a particularly useful, but it's still something you could do. And let me. Okay. So the exercise is the earthquake database based on this data set of earthquakes. That's an interesting data set also. So 23,000 observations of the earthquakes dating from 1965 with 21 columns. And then if we check, D types, we see that date and time are both objects. So meaning, they are strings, and we don't want strings, right? We want to convert them into dates. And so before converting to dates, we see that most of the dates are in this nice format, so month, day, year, but not all of them. So for example, we have a few dates with this long date format. And so if we just specify just a fixed format and try to apply to this field, we're going to get an error. And so one of the things we could do is try to convert that date back to not to convert to string, and then measure the length. And then we see that for all of them except the three, the length of the field is 10, but we have some rogue 3 observations that have this long format, and so we have to decide what to do with them. The easiest way, if it's just 3 of them, the easiest way is just replacing them by hand. So that's, we select select these 3 observations, see where they are, and then replace it by hand with conventional dates, and then we can go ahead and parse this new string with the standard format, and then we get the dates. These are the date times. Yeah, they just ask us to extract the dates, the days of the month from this format, and then plot them. And again, this is the picture we get. This is basically the day of the month that the earthquake happened. And I think, yeah, I think that's it. Yeah, you know, compared to standard pandas pages, like if you go to pandas daytime description, they're like a lot more than this. So I'm not exactly sure why Kaggle decided to focus on a few methods as opposed to like more systematic description of what's in there. But I think, you know, just pandas daytime descriptions, the daytime pages, and I'll post the pages in on Slack, are a lot more informative and useful. Okay, any questions on that?
Thank you, Dimitri. When I was doing this exercise, I was wondering, because I've come across multiple ways of parsing date. So one is you can do it as you read the CSV. You can specify a parse date argument, and you can specify the dates. That wouldn't work in this case because you have some misformatted data.
Yes, yeah.
Another one is you can use what is called a converter as an input to read CSV as well. I don't know if that will work here as well.
Well, I'm not sure. Converter, is that a?
So maybe I can share my screen real quick.
Mm-hmm.
We go at the end, zoom in. So when you read a CSV, you can specify this converter argument, and then you can also specify a lambda function of how you want to standardize, how do you want to transform your date times. That's another way that I also use. And the third way is just to read the data as it is and then transform them after you read them. And I was just trying to figure out which one is faster, which one makes sense, or which one would help you in this case of mislabeled data. I don't think any of them would help you with mislabeled data in terms of what we've seen so far, but I was just curious to say you have like 100,000 records. Is it faster to just do a parse date or converter, or do it later after you read it?
Does converter have to be a lambda function, or can it be any standard Python function?
I think it could be any function.
Then you could do it. Then you could do it that way, right? You could basically account for all different types of formats within your converter.
Yeah, you can go,
I don't know. I don't know that
this one works. This one didn't work. This one didn't work. Okay, this one worked, unless all of them fail.
Yeah, I don't know if it would be fast, but
yeah,
I suspect it would be kind of slow.
George, do you know if you apply those the conversions that you're talking about, if you're doing reading an Excel workbook and then you access the individual pages, can you apply it something like that page specifically? Do you know, or sheet? You know, you're.
Yeah, exactly. When you read a CSV or an Excel, you can specify the page name. I think it's called sheet name.
Yeah, sheet name. And then it only applies to the sheet, that a specific sheet. I mean, you could.
Yeah.
Okay, good.
But now that I remember when I ran this, because I actually got numbers back, it was able to go through those mislabeled data, and I don't know if they actually were read or were thrown away. That's interesting. This one failed for me, and I think this one also failed for me. I'll share this notebook once I take a closer look. Cool, thank you, Dimitri. That was super useful. Cool. Next is David.
Can you see my screen?
Yes.
Okay. So the next thing we're going to look at is character encodings, which if you've ever had to deal with these, they can drive you nuts. But when we talk about character encodings, we mean specific ways that strings are encoded, the characters within the strings. And a lot of times when you're reading in files, the strings come in the form of byte strings, which are actually underneath the data, underneath the in the file system, are actually a series of zeros and ones, bytes as normal, but they're encoded in such a way that you can pull them in and read them as strings. George was enlightening us earlier in the not the chat, I think it was on Slack, that the term for the scrambled things that come in when you use the wrong encoding is called moji bakey. How'd I do on that? Anyway, so
close.
Yeah, apparently a Japanese word, is that right? Yeah, but it's this gibberish you sometimes see where it misinterprets all the characters. Sorry.
It's called mojibake.
Mojibake, there we go.
Mojibake.
Okay. So the standard for character encodings is UTF-8, and for fun I looked up, what that might mean. It's Unicode transformation format. So Unicode transformation format. And Unicode actually has a very long meaning too, which I'll get into in a second. And the 8 doesn't mean version 8, it stands for 8-bit. So that's the character encoding. Unicode actually means, somewhere I saw this, universal coded character set. So really this is the UCCSTF-8 format. But they didn't, that was too long to write, I suspect. But so when we read a Unicode string, which is our normal Python strings that we write, it's a string, and if we want to encode it, it's this UTF-8 encoding that we use. And so this, when we do encode this with that, we'll get a byte string. So when we look at the type, it's bytes. And when you write it out, it looks something like this, where you've got the B in front of the string. It's always a single quote. And then special characters have nice, funny little names that you would never really recognize, usually with backslashes. This is the Unicode format. Giving it the character, the encoding type, and it'll put it back into a normal string that we're used to seeing. So that's how you go back and forth between the byte strings and the strings, so long as you know the proper encoding format that's used. Many old operating systems and other types of producers of data used different types of encoding instead of the UTF-8. One of the most commons is ASCII. You'll see that especially with Microsoft software, you'll see a lot of ASCII characters. And it was suitable for English language, but not really a universal encoding format. So it's not used anymore, but you often run across characters that are ASCII.
Excuse me, David, can you
yes.
scale, zoom your screen up a little bit?
Absolutely.
Thanks.
How's that look?
That's a lot better. Thank you.
Better? Okay.
Mm-hmm.
No problem. And then they go through how you would handle, ASCII if you encoded in ASCII. We guessed that this was, instead of UTF-8, we tried to do it with ASCII, and then we decode it back. We're going to lose this special symbol here because it doesn't recognize that in ASCII, and it's not available properly to encode back. So you're going to make sure that we use the right one. They have a very neat data set that they're going to use. Here's the data set that has the Kickstarter, and it has some ASCII characters in it, as it turns out, but we'll find out, see those later. But it's not all UTF-8, so you're going to get an error message when you just try to read it in with the standard pandas read CSV, because the encoding that uses is UTF-8. And so they're going to apply a neat little package called, module called, I don't know how to say it, but Char detection, I guess is the way to put it. It says Char det. And what you can do is choose, you read the file, which is the file reading utilities of Open, as raw data. And this will be basically that byte strings that you're seeing for. And you can choose how much of that to read. In this case, the error message way back here told us, oh gosh, that was position somewhere. Position 11, I think it is. So it was very early in the file that it ran into a character it couldn't decode. So we know that if we read the first 10,000 characters, we'll probably have enough to cover where that character is, as well as a bunch of other ones, and we can make a guess and detect what the decoding is. So that's what this is doing here, is detecting it. And it gives you a result back where they show the encoding that it's guessed, what its confidence around that detection is. And in this case, it's using not ASCII, but a Windows specific encoding. So then if we go back to do the read with pandas, we can put that encoding in and we'll be successful this time, no error message, and we'll get some results. So here's that file. Was, I think, character 11, but I don't know really. It could be this ampersand that it was having problems with. That's my guess. So they're going to write use this in the exercise. I think that'll be more illustrative for how we can use it. So here we're going to read in very similar to before. We're going to import this same character detector. And we're just going to show some examples. Here's that byte file. It's a bytes, you know. We're going to try to decode it with this funny decoding. And then encode it, and that'll give us back to UTF-8. So that's how you convert it. They just gave us the answer that this is a big 5-TW encoding, and show us how to put it into a standard UTF-8. So we're going to go through and read a file in their data set that has a bunch of non-UTF encodings in it. We're going to use as before, we're just going to read it as raw data. And we're going to look at, I think I did a little test where, let's see. I may not have saved it, but as I recall, it was like character 25,000, something like that, was where it was having issues. And so I read in the first 30,000 characters, thinking that would be enough for the Char detector to figure out what encoding to use. And then I'm just going to put that encoding straight into here and get the answer, and you know, read it and with no problem. So that works. And I went ahead and printed out what that encoding was. It turned out to be the one they used in the tutorial, the same type of thing. Funny that it's always 73%. I don't know. Whenever it detects this, it's always the same confidence. But anyway, the next thing we're going to do is, we showed, you know, once we read that in as a data frame, how can we write it back out to a CSV file that's UTF encoded? Well, that's the standard method that we use. We could put in encoding. I think there's an encoding parameter we could put, but the default is UTF-8. So we're going to do that, and that works. And that was the end of that. Any questions on encoding? Character encodings? Maybe no one's running to it. All right, so we'll move on to the last part in this course, which is inconsistent data entry. Now, this is a very interesting topic. It has to do with people that are, or programs, as I think Chris pointed out earlier, where there's mistakes and you can have misspellings or slightly, spaces or different strange little things in your strings, but usually in the strings. I guess this could apply to other types of objects, but I've seen it primarily used in strings. And they're going to use a couple of interesting modules, this fuzzy wuzzy, which does fuzzy matching on strings. And again, we're going to use our character determinant. So we're going to read in some data about professors in different universities and see what happens. So if we look at it, the thing we're going to concentrate on is country. Here you don't see much, everything's the same, but there'll be some examples, and we'll look at the country the professors are in. So we're going to print out all the values, unique values of that column, and sort them by their name or by alphabetically. And you'll start to see some things in here, like this USA has a space in front of it. I think there's capitalization issues where Germany, I believe, is capitalized here. It also has a space. Down here, it's a lowercase. We've got USA and US of A. We've got South Korea with the space in it, South Korea without the space. So various differences in how things are input into the file. So the first thing we're going to do is try to standardize on things like case. We're going to remove, and later on, if we need to, convert this back to uppercase or anything like that, you can do that at the end. But just to get standard for these programs to work right. So we're going to make everything lowercase. We're going to remove all those white space that's on either the front or the end. I think it's wrong to say it's trailing. It can be, I believe this removes leading white space as well. In fact, I'm 100% sure. And then we're going to use that fuzzy matching I was talking about. So most of you are probably familiar. This is sort of like when you look at multiple strings or values, you start to look at each character by character and see how close they are to each other. And there's ways of specifying a distance between objects, sort of like you would when you're looking at images or when you do things, trying to basically group things in almost, it's used a lot in clusters if you're familiar with cluster analysis, and this idea of things being very similar based on a measure of distance. So here we're going to first get back our countries and their unique. I'm going to use that to go into the fuzzy wuzzy matching. So they give an example here, like Apple and Snapple. They're like 2 changes away, so that would be kind of the distance between them is 2. So you'd have to add an S and an N. Whereas 1 and 1 in and on are only 1 change away, so they would be even closer in similarity because they're just replacing the I. And I thought it was very interesting that there's lots of typos in this description. So maybe they were trying to make the point of inconsistent data entry. I have no idea why this says DA-con.
Same here.
Yeah, it must have been a cut and paste from somewhere else. But we're going to use this fuzzy wuzzy matching to look at the similarity to South_Korea for all our values that are in country. And we're going to pick the top 10 that are the closest, right? And we're going to use this score to sort them. Obviously, when it's an exact match, we're going to see 100. And then the next closest match is surprisingly low, but it's South Korea. Saudi Arabia gets a 43, South Korea gets a 48, and then so forth. So those are the top 10. Once we have that, we can write a function to have a threshold cutoff. Let's say we want to choose 47 here, and everything above that we could convert to what we want it to be, which is South Korea in this case. And so they've written a function here to do that. We pass in our data frame, the column that we're gonna do this matching on, the string that we want to match, which is the value we want it to be, right? And then the ratio is the tolerance for where we're going to cut this off and make the replacement. So first thing we do is we get the columns to the data frame. We get all our unique values of that column, put it in this thing called strings, and we do our matches on our unique string that we're trying to get to those strings. We're going to limit it again to the top 10 and sort it. Ignore the 90 here. I think it should have said 47 or something, but we're going to only do the matches that are above our tolerance. So this is our min ratio, which was 47. And we're going to keep only those close matches. But now we want to go back to our data frame and figure out for those which rows are they in. And so we're going to use the nice pandas utility called isin, and we're going to look for all of those matches and see if they're in there. This actually is going to return back a, I believe it's a series, or sorry, it's a list of Booleans, true or false, and you can use that in the locate method, the LOC method. One of the possible inputs you can put in here, the first indexer for rows is a list of Booleans to say this row's in, this row's out. And with that, the ones that are true, and for the column you want to change, you can set it to our string, which is South Korea in this case. So I had to go through a little bit how the Booleans work in there. And then that's what our function does. It replaces the, this is a in-place replacement for all those specific row and columns where we want to make a change. And here we're actually calling that function. We're passing in our professors. We want to change the country column. Our string to match is South Korea. So once we do that, we can now check again by pulling our unique countries out. And we see now we only have one South Korea, which is the one that we wanted, and it's the way we want it to be done. Does that make sense, what's going on there?
If you want to do this for another country, you have to figure out another threshold, right, David?
You do. Yep.
So you kind of have to kind of exploratory analysis to figure out what is the top 2 or top 3 matches.
Yeah, this 47 is not how to say it, is not automatic, right, or learnable. You've got to kind of look at it to see which one of these, where do the ones that we want to change out fall. And this is a small document or a small data frame. I can imagine, you know, we limited it to 10 here, but if you're working on a really big data set, you may want to do more.
Yeah, I can imagine what would happen if you set it to 35.
Right.
Yeah, I was surprised looking at those results, given that the fuzzy wuzzy is using a Levenstein distance, and you would think that South Korea without the space should only be one edit away, while Saudi Arabia is many edits.
I would have thought it would have been very high. Yeah, I'm a little surprised, but again, this is not, you know, they do point this is not a perfect thing, and you know, it's a convenience utility in a way, rather than you having to look through and hand replace, or at least write code to hand replace all of these, right?
Yeah, it's been a long time since I looked at Levenstein, but spaces kind of throw it off too. If it looks like, you know, if it thinks it sees 2 words, it treats it differently, doesn't it?
Could be, right? So maybe.
It's been a decade since I got deep into the details of it, so that's as much as I want to say without talking out of my ass.
I don't know. I think just missing a space like that is just a distance of 1.
Yeah.
So they should be close. I don't know why South Korea is so far without the space is so far away.
Yeah.
Probably just because it shifts all like half of the letters over.
Maybe moving everything.
Maybe it's because somebody, you know, in moving the 2 words together, it violates the DMZ or something.
That's
something funny. It should be a distance of 1. It should be like really close. I don't know what's going on.
Yeah.
Does anybody, this string matching and this sort of stuff is age old. There should be some really slick packages to handle this by now. Does anybody know of like, say handling addresses and matching names?
So I have a much more advanced way to do this that I'll talk about at the end that maybe might alleviate the need to even do this.
Okay.
But yeah, I'm sure there's something better than fuzzy wuzzy. I don't know, maybe not. All right, so I'll move on to the exercise. In the exercise, we're going to look at the same basic database of professors, the information. We're just going to look at, they go through and show how it works again for South Korea. And then we're going to look at a different column called graduated from. And here we've got a lot of data. I printed it out just for us to see. And if we want to look.
David, do you mind closing back the right panel? You have a right panel open. Just there you go.
Hold on.
Oh no. There you go. Thank you.
I know. I had to get the picture of who's talking out of the way. So there are some, they pointed out a couple examples. Here are some examples where there's spaces in there. There's probably quite a lot of repeats with different. So you can imagine there's a lot of strange things. In fact, here's one of those funny encoding characters. Somehow that slipped through. They didn't ask us to deal with that, and I doubt that it would have been, if I'd seen this, it would have been interesting to apply the fuzzy wuzzy and see if we could correct that. I bet we would, but anyway, might throw it off. So we're asked to do some pre-processing, basically to strip out the spaces on each side, trim the string. So we just use that straight strip to get rid of that. And then we go back to looking at countries again. And in this one, you see the things, we see some strange countries like Urbana, which I guess maybe that's a sign they're very independent there. But we've got USA and US of A, and we're going to look at that. So they're asking us to convert US of A to appear as USA instead. So we'll look at how we do that. It's very similar to what we did with South Korea. Here we're going to get all the matches that are close, limited to the first top 10, and then we're going to apply our function that we wrote to actually replace it with USA. Here, I printed out just for our sake the matches. USA is direct match. Here with having the of inside, we've got a 75, which is actually better than the South Korea score I think we saw before, right? So even though we've got two of them that are off, we get a better score. So I used that and put in 74 here, and that worked and everything worked. So so back to Kathleen's question. I think it was Kathleen. One thing that I would consider doing is so here's the type of data they have right in here, and it's a lot of these are what I would consider categorical, right? These values, these strings are categorical, right? So you could go through the trouble of fixing the misspellings and some of that stuff. Or what I would typically do is treat these categorical columns with embedding. And then I would hope that my learned embeddings would put things like US of A and USA very close, right? So the learned embeddings would be very, very similar. And that way I wouldn't have to worry about making, these kind of changes. So that might be another approach.
Is there a way to verify that actually works though? I mean, I understand the theory and understand embeddings, but how do you know that it worked?
So yeah, you would want to so you can obviously do out put out the embeddings and look at I guess some of the t-SNE things and see if they're close, right?
Mm-hmm.
See, you can look at the vectors that are learned and see how close they are.
Got it.
Yeah.
I think this is where like 75% of the 80% of the pre-processing and data prep comes in.
Yeah. So
I actually love doing it, but it takes so much time that I always feel like I went down a rabbit hole after 3 days with regex or whatever.
Right. And the last point I was going to make was, Dimitri kind of made this too, that that you want to, anytime you change your data, you want to make sure you're not losing some information that might be, almost like metadata around why that data was input wrong or why that data was missing. And we did try something, I think, in one of our feature engineering courses where when we made a change, we added a new column to record the rows where we made the change. Mm-hmm. And then we fed that into our models for another feature, an additional feature. And I think that's worth considering sometimes when you're doing these type of data cleaning, that you also track what you cleaned as a feature, just in case there was some importance there that you might have lost, that you can still keep track of that. Just an idea.
Oh, it's a good one. And depending on the data that you got, that could be pretty important.
You were doing any kind of sentiment analysis or, the natural language processing. Somebody who says US of A is different from somebody who says USA.
Right. So maybe there's meaning in that. Yeah, exactly. Yeah. Depending on what you're doing. Any other questions on?
Well, this was interesting. And just a little bit of heuristic, I would say, on figuring out the threshold. And I don't know if it scales to other fields except for country. Like, those numbers to me didn't make a lot of sense to me. I don't know if there were percentages instead of edit distance numbers like 48, 100. I don't know.
Right.
So maybe 48% was 48% of them was the same. But then again, South Korea with space and without space is not 48% the same. Cool. Something on the chat that you brought up, Robert, if there are no other questions, I have a couple of questions. Of reducing the mean and dividing by standard deviation, you said that it doesn't change the shape of the distribution. So you need to do some kind of, you said, third moment transformation for the shape to change. That was interesting to me.
Right. If you want to change the shape of a numerical distribution, your standard scaling is just going to move it so that it has the same shape, but the standard deviation of 1.
So dividing by standard deviation will basically change.
It's a constant, so you're just multiplying it by a constant.
Yeah.
You're applying a linear function to your data.
Got it. And I had another question that I think you, David, brought it up when Dimitri was covering his notebook of encoding or transforming the target variable, the label Y. Is there any rule to that? I mean, I think so far from what we've seen is when you transform or the X matrix, right? Your features. So is there any rule when you do the Y and you look at distribution like Dimitri was looking? Like, I'm curious.
Well, obviously for visualization, yes. But the only other place I've seen really is you sometimes get faster convergence, better convergence of your model when the distribution of the target matches the activation function of your final prediction, right? So like, if you're doing regression and you're using sigmoid there, right? Sometimes you see better results when you map from like 0 to 1 your targets. Maybe Robert knows the reasoning behind it, but.
You're saying your target variable Y should match, the distribution should match the output range of your activation function. Usually that's a good idea.
Yeah.
I think what you're referring to is just the fact that you want to have an activation function that's compatible with your output, right? If you're predicting a probability, you want to have a sigmoid because that maps you to the correct range of values.
Yep.
And if you have, let's say, negative and positive values, do you somehow scale them to like, I don't know what to do, like
linear output layer.
Linear? Cool.
My only point was that if you do for some reason find it advantageous to scale your targets, you just need to make sure that when you're putting out the real prediction, you unscale them back to. Otherwise, your prediction.
So your transformation should be reversible, basically, right? You cannot do a.
If you do it for your targets, yeah, and you want to. Yeah.
Got it. Cool. Thank you.
All right. If there's no further questions on this, thank you for joining us all this evening. We've learned a fair amount about inconsistent data entry, data cleaning, dates, character encodings, and all the stuff that trips us up on a day-to-day basis, including saying that. So thank you for joining us all this evening. Our next event is this Friday at 7 o'clock. We're going to be doing the Geospatial course, another from the Kaggle series. And I believe we have Svetlana Levitan is leading that one. And I think, is it George doing the last two?
Yeah, I think so, yeah.
Wait, is Svetlana's doing that? I thought I was doing the geospatial.
She's doing half.
Well, if you want, you can do it. That's fine. I haven't actually.
Oh, if you want, you could do it too.
No, we usually have two people covering it. It's just for diversity, so you can both do it.
Okay. So Svetlana, you and I can talk offline about splitting it up.
Okay, we can talk. You are on Slack, right?
Yes.
Okay.
Awesome. Wonderful. And then next week, we have changed the schedule a little bit with Thanksgiving in mind and the fact that many of us still aren't really traveling or doing much during the pandemic anyway. So we're going to do a happy hour on Wednesday evening. No content from the courses, but feel free to join us at the usual hour. And then Friday will be a bit of a diversion through the micro challenges course. That's Friday the 27th. So,
thank you, Robert. Dimitri, I need to know, how deep did you go on the micro challenges?
I just looked at the data set. I haven't started yet. Yeah.
So you have some time to prepare for them, because I know you're doing one of them. Cool.
Thanks, Dimitri. Thanks, David. Really nice presentations.
Thank you, friends. Thank you, Dimitri. Thank you.
Thank you.
Robert.
Good night.
Thank you very much. Good night.
Have a good night.
Everybody, see you next time.
Good night, guys.
Bye.